Welcome to our Quantum Deep Dive.
Great to be diving in.
Today, we're embarking on a journey really into the deep end of theoretical physics. We're exploring a particle that could, well, potentially change everything we think we know about the universe.
That's the one, the Gravitino.
Exactly. It's this hypothetical elementary particle.
Yeah.
The idea is it might just be the missing link between gravity and the quantum world.
And just so you know where we're drawing from today, our deep dive is based heavily on the really insightful essay, Gravitino Hypothetisches Teilchen der Supersymmetry by Jürgen Schneepapp.
Right.
Our goal, like always, is to pull out the most important stuff, the key ideas, and maybe some surprises from the material, just for you.
Okay, so it comes from this concept called supersymmetry, which sounds pretty mind-bending itself. It's supposed to connect gravity, the big stuff, with the quantum world, the tiny stuff.
Mm-hmm.
So let's unpack this. What exactly is a gravitino, and why is it such a big deal?
Well, fundamentally, the Gravitino is imagined as the supersymmetric partner to the graviton.
The gravity particle.
The hypothetical gravity particle, yes. Its existence is predicted by theories that try to extend the standard model of particle physics. The main motivation is trying to unify gravity with quantum field theory, get them talking the same language, so to speak.
And here's where it gets really interesting, right?
Yeah.
Its spin. Unlike most particles we know, the gravitino is supposed to be a spin 32 fermion.
Yeah, that's pretty unusual.
We know photons are spin 1, electrons are spin 12, but spin 32, that feels different. It suggests something deeper going on, maybe.
It definitely points towards a more complex symmetry. That specific spin, 32, is essentially dictated by supersymmetry, or SU-EY.
Yeah.
SU-EY is this framework that suggests every particle we know has a kind of hidden, heavier partner, a superpartner. It's an attempt to solve some big puzzles in the standard model.
Like the hierarchy problem.
Exactly, like the hierarchy problem, basically. Why the Higgs boson isn't way heavier than it is. SUI offers a potential explanation for that. And the idea of the Gravitino itself popped up back in the 1970s. People like Daniel Friedman, Sergio Ferrara, Peter van Nieuwenhuizen, they were the pioneers. They built the first consistent supergravity model in 76.
Oh, okay.
And in that model, well, the theoretical mediator of gravity is a massless spin 2 boson. SUSY says it needs a partner.
And that partner has to be
a spin 32 fermion.
Yeah.
Which is a gravitino. It completes the picture within that supersymmetric framework.
Okay, unique spin, partner to the graviton. What about mass? Does it have mass? Is it heavy, light?
That's one of the really intriguing parts. If supersymmetry was perfect, totally unbroken, the gravitino would be massless, just like the graviton is thought to be.
But it's probably not perfect.
That's what most realistic models suggest, yes. Supersymmetry seems to be spontaneously broken in our universe, and if it's broken, the gravitino gains mass. But here's the kicker. We don't know how much mass. It can be incredibly tiny, like 10 to the minus 5 electron volts, or it could be really heavy, up in the GeV or even TeV range, similar to particles the LHC is looking for.
Wow, as a huge range.
It is. It all depends on the energy scale at which supersymmetry breaks.
Okay, fascinating. So that's the big picture idea. Let's dig a bit deeper into its actual properties. We mentioned the spin.
The spin 32, yeah.
Oh.
Mathematically, it's described by something called the Rita-Schwinger field. It just behaves differently than spin 12 fermions, like electrons.
And charge.
Electrically neutral. Just like its partner, the graviton, which of course makes it invisible to anything looking for electromagnetic signals.
Right, no light interaction.
No light interaction. And the mass, as we said, varies wildly. It's linked to something called the super Higgs mechanism, kind of analogous to the regular Higgs mechanism, but in the context of SUSY breaking. The formula is roughly mg/fmp, where F is the SUSY breaking scale, and mp is the Planck mass.
Okay, so mass depends on when SUSY broke. What about how it interacts, besides gravity?
Gravity is its main thing, which makes the interaction incredibly weak. That's the detection problem in a nutshell.
Mm-hmm.
But in SUSY models, it would also interact with other superparticles, things like neutralinos, gluinos, leptons, the hypothetical partners of neutrinos, gluons, and leptons.
So what does this all mean for the bigger picture of physics? You mentioned supergravity.
Exactly. Supergravity, or SUSY. Think of it as Einstein's general relativity, but with supersymmetry built right in.
Merging gravity and SUSY.
Precisely. And in SU-array, the gravitino isn't just some side effect. It's actually the particle, or the field, that mediates local supersymmetry. It's fundamental to the theory itself.
And that's huge for quantum gravity, right? The holy grail of unifying everything.
Absolutely. Quantum gravity is one of the biggest mountains left to climb in physics. Supergravity, with the Gravitino playing a key role, is seen as a really promising path forward.
Could it help unify all four forces?
That's the hope, especially within string theory, which is arguably our best candidate for a theory of everything. Gravitinos are an essential ingredient in most string models.
Okay, shifting gears a bit.
Yeah.
If this particle exists, what does it mean for the cosmos, like the universe itself, especially way back in the beginning?
Ah, yes. This leads to something called the Gravitino problem. It's a potential headache for cosmology.
A problem? How so?
Well, the idea is that if gravitinos were produced in large numbers in the very early universe, like after the Big Bang, during the reheating phase after inflation,
Right.
their decay later on could cause serious issues. If they live for a relatively long time, seconds, minutes, even years before decaying.
That's long in cosmic terms, early on.
Very long. Their decay products could basically wreck primordial nucleosynthesis.
The process that made the first light elements.
Exactly. Hydrogen, helium, lithium. We have pretty precise measurements of how much of each should have formed. If gravitinos decayed late, they'd inject energy and particles that would mess up those calculated abundances. We wouldn't see the ratios we observe today.
So their existence puts limits on the early universe.
It does. It suggests the reheating temperature after inflation couldn't have been too high. Otherwise, you'd produce too many gravitinos and run into this problem. Roughly, you need the temperature TR to be less than about 109 Chevi.
That connects to dark matter too, doesn't it? Could this elusive thing be the stuff we're looking for?
It absolutely could. The Gravitino is actually a very compelling dark matter candidate, if it's the lightest supersymmetric particle, the LSP.
The LSP, why does that matter?
Well, if it's the LSP, it generally can't decay into anything lighter within the SUSY framework, making it stable over the age of the universe.
Okay, stability check.
Check. Then it's electrically neutral, so it doesn't interact with light. It's dark.
Dark, check.
And it interacts very weakly, mostly via gravity.
Weakly interacting, check. Fits the bill.
It really does. There are different ways it could have been produced in the right amount, too, either thermally in the early universe or non-thermally from the decay of heavier SUSY particles later on. It fits many dark matter scenarios quite well.
And it's not just about the early universe or dark matter, right?
Mm-hmm.
You mentioned it could even influence the expansion of space-time itself.
Indeed. Its influence could be quite broad. Gravitinos could have affected the energy density during inflation. Depending on their mass and properties, they could act as dark radiation, adding relativistic energy content.
Affecting how the universe expanded.
Potentially, yes. They might also play a role in how large-scale structures, like galaxies and clusters, formed. And there's even speculation they could interact with dark energy, maybe influencing the cosmological constant lambda that drives the current accelerated expansion.
Wow. And you mentioned string theory again.
Yes. In string theory and M theory, gravitinos are deeply embedded. They connect two ideas about extra dimensions. Some models suggest that what we perceive as dark matter could actually be gravitino modes existing in these hidden higher dimensions.
Okay, mind officially bent. This particle sounds incredibly important. But the million-dollar question, how do we actually find it if it's so weakly interacting and neutral?
That is the monumental challenge. Direct detection is... well, it's borderline impossible with current technology.
Why so hard?
Primarily that extremely weak coupling. It barely talks to normal matter except through gravity. The chance of one interacting inside a detector is just vanishingly small.
Like catching a ghost.
Pretty much. Plus, it's neutral, so no electromagnetic handle to grab onto. And then there's the mass problem. You're searching over this enormous possible mass range. You don't know where to tune your detector, metaphorically speaking.
A Herculean task, then. But we're not totally in the dark, are we? You mentioned indirect ways.
Exactly. We have to be clever. Indirect detection is where the action is right now. We can look for its fingerprints on the cosmos.
Like the nucleosynthesis thing.
Precisely. Checking those light element abundances very carefully. Or looking for tiny, subtle patterns and isotropies in the cosmic microwave background radiation, the Big Bang's afterglow. The gravitino's presence could leave faint marks there.
What else?
We can look for signs of dark matter decay or annihilation. If gravitinos make up dark matter and occasionally decay, maybe if SUSY is slightly broken in a specific way or if it's not quite the LSP, they could produce high-energy gamma rays or neutrinos that telescopes like Fermi or IceCube could potentially spot.
And particle colliders, like the LHC.
Yes, that's another key avenue. If SUSY is real and particles like squarks or gluinos are produced at the LHC, they would cascade decay down to the LSP. If the Gravitino is the LSP,
it escapes the detector.
right, it zips out unseen, carrying energy and momentum with it. What the experiments see is missing energy. The energy going in doesn't match the visible energy coming out.
Like an invisible thief.
Kind of. A typical signature might be seeing, say, a quark and a photon flying out, but with missing momentum, suggesting a decay chain like squark to quark plus neutralino, then neutralino to photon plus gravitino. That missing energy is the indirect clue.
What about future tech? Anything on the horizon that might give us a better shot? Quantum sensors?
That's a really exciting frontier. Things like gravitational wave detectors, maybe not LEGO, but future space-based ones like LISA, could potentially detect a faint background gravitational wave hum left over from gravitinos in the very early universe.
Wow.
And then there are ultra-precise experiments using things like superconducting circuits or atom interferometry. These quantum sensors are becoming incredibly sensitive, and maybe, just maybe, they could detect the minuscule gravitational influence or other tiny effects of something like a gravitino passing by. It's a long shot, but definitely worth exploring.
Okay, so suppose we do find it. Against all odds, we get convincing evidence. What happens then? What's the impact?
Oh, it would be revolutionary. Absolutely game-changing. First, it would prove supersymmetry exists. That alone would be a Nobel Prize-winning discovery, opening up a whole new layer of reality beyond the standard model.
Right, a new physics framework.
Exactly, and it would likely solve the dark matter mystery, or at least a major part of it. Understanding what 85% of the universe's matter is would be phenomenal.
And future experiments.
Future colliders, like the proposed FCC or ILC, would become essential. We'd need them to study the gravitino's properties in detail, map out the whole spectrum of superparticles, and really understand this new physics.
So despite all this incredible potential, there are still some big fundamental questions hanging over it, right? It's not a sure thing.
Not at all. Big questions remain. The biggest, perhaps, is supersymmetry even real? The LHC hasn't seen direct proof yet, which has tempered some enthusiasm, though it hasn't ruled it out.
So the foundation itself is still hypothetical.
Very much so. Then, even if COSY is real, is the gravitino stable? If it decays, even very slowly, it's less likely to be the bulk of dark matter. And what is its mass? Nailing that down is critical for knowing how to search for it.
And its ultimate role.
That's the deepest question. Is it just another particle, or is it truly the key linking quantum mechanics and gravity? Does it connect dark matter and gravity in a fundamental way? Does it hint at multiverses? We just don't know. These are the frontiers.
So the gravitino, it's hypothetical, yes, but it's a concept that could just fundamentally rewrite our story of matter, dark matter, even space-time itself. It really feels like a cornerstone for these big unification ideas like supersymmetry and supergravity.
It truly is one of the most exciting theoretical ideas out there. If it's discovered, it wouldn't just be filling a slot in a particle table. It would signal a paradigm shift, potentially unifying forces we've struggled to connect for decades. Imagine really understanding how gravity works at the quantum level. The gravitino might hold the key.
Well, thank you for joining us on this really deep dive into the gravitino's world. We hope you, listening out there, are as intrigued by these quantum puzzles as we are. Definitely keep exploring these ideas.
Absolutely.
And remember, our exploration today was grounded in the fantastic essay by Yurgo Schneepat.
A great starting point if you want to learn more.
Definitely. And if you are fascinated and want to dig even deeper, you can find more information and explore related topics over at schneepat.de.
Well worth a look.
Until next time, keep diving deep.